So we're on day 2 of our 9.5 notes. We talked about the alternating series test yesterday. And so today we want to get a little more specific about convergence. So there are 2 types of convergence, absolute and conditional. Absolute is kind of what it sounds like this converges absolutely, no matter what. That means alternating or not, this series converges. So, for example, and we're going to get into this, but a quick example here is think about like the sum of 1 over n to the third. That converges, right? It's a p series. Also, the alternating version of that, so like -1 to the n over n to the third, that's going to converge because it's alternating, its terms are decreasing, and its limit is 0 at infinity. So this converges no matter what, whether it's alternating or not alternating. Conditional convergence is when something only converges if alternating. The classic example that I always think of is the harmonic series. The harmonic series diverges, but as soon as you make it alternate, it converges because it's alternating. Its limit as n approaches infinity is 0, and it's decreasing. Each term is smaller than the one before it. So we're going to kind of formally do this, but again, we're going to just that's kind of the main idea here. So the theorem is if the series of the absolute value of a sub n converges, then the series a sub n, the sum of a sub n, also converges. But the converse is not true, so we have to be careful. So just because we know that the sum of a sub n converges, we can't say the sum of the positive version converges. And I'm just going to go back to my my harmonic series. So the alternating, just because the alternating series converges does not guarantee that the positive or non-alternating series converges. Not guaranteed. So again, that's called conditional convergence. This series converges on the condition that it's an alternating series. All right, so officially, the series of a sub n is absolutely convergent if the actual series converges, the alternating series converges, and its positive counterpart converges, and the alternating series is conditionally convergent if the alternating series converges, but the positive version diverges. So again, that's that harmonic example. All right, so let's just look at some examples. We're going to determine converge or diverge using the alternating series test. And then if the series is convergent, we're going to try to classify as conditionally or absolutely. So for this first problem, let's just do a quick check. Is it alternating? Yes. These are kind of the conditions, by the way. We usually have to list them because alternating series, they do show up in free response questions. Anyway, so it's alternating, check. The limit as n approaches infinity of, take off the alternating piece, n factorial over 2 to the n is not equal to 0. That's equal to infinity. So I can stop right here on number 1 and say, actually, this alternating series diverges by the nth term test. Remember, the alternating series test is only a test for convergence, and the nth term test is only a test for divergence. So as soon as you show that the terms in your series are not approaching zero, it means that you will have the sum that just keeps growing and growing and growing. All right, so done with that one. For number 2, we have an alternating series. Check. The limit as n approaches infinity of 1 over square root of n is equal to 0. So that's a check. And finally, are the terms decreasing? Is 1 over the square root of n plus 1 less than or equal to 1 over the square root of n? And yes, I would say that's true as well. All right, so since all of these things are true, I can say that this series converges by the alternating series test. Now that I know that it converges, does it converge conditionally or absolutely? So to check that piece, look at the series without the alternating part on it. So just look at the series from 1 to infinity of 1 over square root of n. That's a p series where p is 1/2. And so that is a divergent p series. So back to my original alternating series, it converges by the alternating series test, but only conditionally. On the condition that it's a p series, but it's got to be alternating for it to actually converge. All right, next one. -1 to the, oh, that's fun, n times n plus 1 over 2 over 3 to the n. All right, so let's check. Is it alternating? Let's see. I guess I have all this room. I don't know why I was crunching everything in there. So I'm going to come over here. Is this alternating? If you plug in 1, you'll get +1. If you plug in 2 times 3, let's see. It's easier to do n squared plus n, I think. Let's see. You get 1, because you get 2 over 2. And then if you plug in 2, you get 6 over 2, which is 3. So that's going to be negative. Yeah, I think so. And then if we plug in 3, 9 plus 3 is 12, over 2 is 6, positive. Okay, so yes, this is alternating. I've convinced myself of that. And the limit as n approaches infinity. Remember, this whole ugly exponent here is just the alternating piece. So it's just 1 over 3 to the n. That does equal 0 because it's 1/3 to the n power. Any fraction between 0 and 1 decreases to 0. So check. And is 1 over 3 to the n plus 1, is that less than or equal to 1 over 3 to the n? Yes, because this is the same as 1/3 times 3 to the n down there. So, or 1 over 3 times 3 to the n, I should say. So yes, that is going to be overall a smaller fraction. Okay, so I know that this converges by the alternating series test. All right, now does it converge conditionally or absolutely? So check the series of just 1 over 3 to the n. That converges by the geometric series test. So this original alternating series converges as its alternating self, and it converges as its positive self. So this thing converges no matter what. It converges by the alternating series test. Absolutely. All right, and then, I think our final example for today, could it be? Yes. As far as my notes go, our last example for today, okay. Is this one alternating? Yep. -1 to the n. Is the limit as n approaches infinity of 1 over natural log of n plus 1, is that going to equal 0? Yes, because even though it grows slowly, the natural log of n plus 1, that is infinity. It just is slow about getting there. So, yep. And then are the terms decreasing? So is the natural log of n plus 1 or n plus 2, 1 over that, is that less than or equal to 1 over the natural log of n plus 1? I would say yes. The natural log of a slightly bigger number in the denominator will make a smaller overall fraction. Okay, so now what are we looking at? Well, we need to check, converges. We know that this converges by alternating series test. Okay, done. So now the conditional or absolute part. So when we're comparing it to its positive series, all we're doing right now is cutting off the 1 over a natural log of n plus 1. But that's not a p-series, and it's not geometric, and I don't want to have to do like integral test, because then we'd have to do by parts, right? Because it's a natural log. So remember, you can also think of limit comparison test or direct comparison test. So let's think about that. Let's compare it to something. Well, I want to compare 1 over natural log of n plus 1 to something that I know for sure, like 1 over something. I need this to either be something that's guaranteed to be a bigger value than natural log of n plus 1 or a smaller one. As far as like functions that grow slowly, natural logs are kind of at the bottom of our list. So I'm just going to have to pick something bigger. The next rung up on the ladder of like slow moving functions is just something linear. So maybe I'll just put n, because I know about the 1 over n, the harmonic series, right? So n will be, in the long run, n will be a bigger number than natural log of n plus 1. Maybe not for the first couple of values, but that's okay. So eventually, this fraction on the right is smaller, less than or equal to the fraction on the left. Okay, so what do I know? I know that the sum from 1 to infinity of 1 over n diverges. It's the harmonic series, or it's a p-series with p equals 1. All right, and it is the function on the bottom, right? And it's diverging, it's pushing up. So I think we can go ahead and say, by direct comparison test, we know that the series, actually, I don't want to say series, let's be more specific. We know that the sum from 1 to infinity of 1 over natural log of n plus 1 diverges, because the smaller series is pushing up, diverging on the bigger one. All right, so since we know that the alternating series converges, but the non-alternating, the positive version, diverges, then this converges conditionally. Alternating series test and remainders, and especially the remainder part, and this idea of conditionally and absolutely, they are definitely going to pop up on our AP test in both parts usually. The remainder part tends to be in the free response, and this conditionally absolutely stuff tends to be in the multiple choice.